Hi, everyone, and welcome. And thank you for joining today's webinar, Graphs, the New Realm for Access Management. My name is Pat Wall. I'm the Director of Product Marketing at Neo4j. I'm joined by a very special guest, Dr. Seyed from Nulli. I have a few housekeeping items I'd like to get started. First, please submit your questions in the questions tab above. We're going to answer a few questions, and hopefully we get to all of them, but we might not to. If you're really eager and you really love graphs and security and you need someone right away to answer your questions, feel free to send them to webinar@neo4j.com, and we'll get someone to help you right away. And with that, I'd like to hand it over to Dr. Seyed.
Thank you. Thanks, everyone, for joining. In this webinar, I'm going to give you a high-level summary of how graphs actually changed identity and access management. I'm a senior identity and access management architect for Nulli. So what I'm going to do, I'm going to first talk about who Nulli is and what we do at Nulli. Then I will talk about identity and access management. I will try to give you a very simple definition for that. And then I move to basically talking about how relationships changed identity and access management. And then finally, I will talk about two stories. These are two real projects that we had with our clients to work on problems, identity and access management problems, where we needed to bring in graph databases, and in particular Neo4j, to solve those problems. So as I told you, I'm working for a company called Nulli. We are located in Calgary, Alberta, Canada. And this picture you see here in this slide, it's from Calgary downtown. We've been working on identity and access management problems since 2000. And since 2013, we actually started integrating Neo4j into the identity and access management solutions that we have been providing for our clients. We are partnered with Neo4j and also ForgeRock. You know about Neo4j, and ForgeRock is basically a vendor of IAM services, for example, services for authentication, authorization, and directory services, things like that. At Nulli, we try to propose innovative, unique solutions to identity and access management problems, and we've been working on, very complex problems in this area. We have deployed over time, more than 1 billion of identities on behalf of our clients, and we have more than 100 global IAM clients. Okay, so now let's talk about identity and access management and what that means. What you see here in this slide is a very simple sentence for defining identity and access management, which is basically about who can perform what actions on what resources under what conditions. In other words, when we talk about identity and access management, we talk about platforms that they let you to identify users, devices, and in general things, any identity basically, and then allow the identities with the right privileges to access protected resources. This is called identity and access management. Now let's see how relationships change access management, and let's talk more about the role of relationships in identity and access management. In a traditional identity and access management platform, sometimes you deal with roles. For example, you define a role for an employee, and that role could be something like finance manager, which means that employee can probably access some finance documents. So that is called role-based access control. Sometimes you deal with attributes. So you want to say, if a user is at least 18 years old, then he or she can access a resource and see, for example, a photo album. Sometimes, you need to work with access rules. For example, you can say that if you are receiving a request to access a resource, and that request is coming from an IP address, a particular IP address, then we're going to grant or reject it. So these are access rules. Now, in a more modern identity and access management platform, we have a new paradigm. We need to also deal with relationships. Now, when we get a request from a user to access a resource, we need to look at how that user, how that identity is connected and related to other identities in the platform. And since a few years ago, when the idea of IoT, Internet of Things, was proposed, we've seen that more frequently that there is this platform with millions of identities and things like users, cell phones, smart cars, or software services, and these are all related to one another. And when you want to decide whether a user can access, let's say, a smart car, you need to look at the relationship. You need to find out whether, let's say, this user has some sort of a path through multiple relationships to that smart car. So this has made the problem of dealing with relationships in identity and access management more complex over time. Now that we know what identity and access management is and how relationships change this problem, let's talk about two real stories. These are, again, as I mentioned earlier, these are real projects that we have had with our clients. And the first one is about role engineering in role-based access control. This project was with a big financial institute. They were using an entitlement-based access management system, which I'm going to explain in the next slide. And we had two goals in this project. The first one was to propose a solution to simplify maintenance of such a system. And the second one was to propose a solution for supporting access certification. And access certification typically means that you look at your users, you look at their privileges, and then you want to make sure that these privileges that have been assigned to users, these are the right and correct privileges, and they really need to have these entitlements and privileges. In an entitlement-based access management system, entitlements are basically privileges. You give an entitlement to a user to basically authorize them to access a protected resource. Now the question is, how are these entitlements are created and assigned? In an ideal world, these entitlements are assigned based on HR attributes of users and employees. For example, if you have a new hire who's going to work in this particular department with this job title, then based on that, you will give him or her some entitlements. But unfortunately, that's not always the case. What we have seen so far is that mostly these entitlements are assigned based on ad hoc access requests. So someone needs to access something for purpose, and they submit a ticket or request, and then their manager approves them. So there's no real logic behind approving this submit ticket and this submitted access ticket, and there may not be any reason or any connection between the HR attributes of that user and the entitlement that has been assigned to him or her. This causes a few problems. First of all, we will end up with a very fine-grained access management system where entitlements are very fine-grained and they are actually too many, which made for this particular client, maintenance of this access management system very difficult and hard. And these entitlements, they tend to be assigned randomly, and they do not match with job responsibilities. These are the issues that this client had with their entitlement-based access management system. And the goal was to move from fine-grained entitlements to coarse-grained roles that are more high-level, and they are collection of maybe some fine-grained entitlements And we also wanted to be able to do access certification, to look at the data, users and their entitlements, and decide maybe some entitlements should be revoked or not. So these two were the goals of this project for us. Now let's try to define the problem in a more formal way. So as I mentioned earlier, we have a set of users. All these yellow nodes are the users. And then we have a set of entitlements, and these entitlements are assigned to the users. And the goal for us is to basically look at these entitlements and their connections to the user and try to group them to some high-level roles. And a role will be a collection of entitlements, basically. If you look more carefully at this graph, you will notice that this is actually a bipartite graph. A bipartite graph is a graph where you can basically divide your vertices, your nodes, into two separate sets, and all the edges are going from one set to the other, which is what actually we see here. And for us, as I mentioned, the goal is to find similar entitlements that are maybe assigned to the same set of users. So if we have some entitlements, for example, E4, E5, and E6 in this sample graph, we can see that they are assigned to exactly same users. And that means maybe we can define a role for them. And again, if you look more carefully, you can see what we are trying to do. We are actually trying to do, trying to find complete bipartite subgraphs. A bipartite graph is complete if we have an edge between every node in one set and another node in our target set. So we want to have a complete subgraph here. And then if we can find such a complete bipartite subgraph, we can define a role for those entitlements in our subgraph. And we end up with something like this. And you can see that it significantly simplifies what we have here, the whole graph of users and entitlements. And we don't want to find any complete bipartite subgraph. We want to find the bigger ones, because if we just find any complete bipartite graph, we may eventually end up with too many rows, because there might be too many complete bipartite subgraph. So the problem is now to find maximal complete bipartite subgraphs. And we know that this is an NP-complete problem. So we decided to actually come up with an alternative solution to achieve what we are showing in this slide. So let's go back to the problem. The problem was to look at this graph and then try to group entitlements and form roles. We actually found out that if we use a similarity measure called Jacquard similarity, which is a value between 0 and 1 and is calculated using this formula, we can achieve the same thing. We want to find a Jacquard similarity between all entitlements. And based on this formula, if Jacquard similarity between two entitlements is 1, that means they are assigned to exactly same users. And that is basically what we saw in the previous slide. That was the goal, to find entitlements that are assigned to the same set of users and then define a role for them. So this is what we are trying to do. Now I'm going to actually show you how we can do this in a real world when we are using Neo4j to store our users, our entitlements, and our user entitlement assignments, which are edges between users and entitlements. So I'm going to share my screen. What you see here, this is called Bloom. It is a visualization tool provided by Neo4j, and I'm going to use it to just show you our sample graph that I'm going to use for this demo. The first thing I'm going to do, I'm going to make sure my data is up to date. I have users and entitlements in my subgraph. And this is what you see. Green nodes are entitlements, yellow nodes are users. For example, here you can see that we have a user with 3 entitlements. And I can also see that these 3 entitlements, they are assigned to only one user in this enterprise. So that maybe tells me something. It tells me that there are some responsibilities, some entitlements that can be exercised only by this particular employee. So this could help me in the access certification phase. Maybe there is something wrong here. Maybe these entitlements should be assigned to some other users too. Or in this other subgraph, you can see that all the entitlements, the green nodes, are connected to all the yellow nodes, the users. And that tells me that maybe this is a good candidate for defining a role, because we have this complete bipartite subgraph that we can use for defining roles. So now that we see how our graph looks like, what I'm gonna do, as I showed to you in my slides, I'm gonna calculate the Jacquard similarity between my entitlements in this graph. And for doing that, I have prepared a Cypher query. What you see here, you can see that I'm running a function called node similarity. And this is actually included in Neo4j Graph Data Science library. This library has a lot of graph algorithms that you can use for different purposes. And in this example, I'm going to use the node similarity algorithm to find Jacquard similarity between every 2 entitlements in my graph. So I'm going to run this. And then I will go back to my graph. I just changed my perspective to show you a different view of my graph. I refresh my data, and I make sure I can see connection between entitlements. So what you will see in a second is basically some new edges that have been added to this graph. And these are shown using red color. All these red edges are basically Jacquard similarity between 2 entitlements. For example, if I zoom in here, you can see that we have 3 or 6 red edges between these 3 entitlements. And that shows that the Jacquard similarity between them is 1, because they have been assigned to one single user. They share the same set of users, and for that reason, Jacquard similarity between them is 1. So this is now a good candidate to define a new role. Or in this other subgraph, we have lots of red edges because these entitlements are assigned to all these users. This is a complete bipartite subgraph, a very perfect situation for defining a role. In this other subgraph here, what you can see that for most entitlements, we can see lots of red edges because they are assigned to the same set of users. But I have a few entitlements, for example, this one, that they are not assigned to all users in this subgraph. Again, this could be an insight for me. It could tell me that now that we have kind of a complete bipartite subgraph, why these 4 other entitlements are not connected to all the other users, and they don't have those red edges, connected to other entitlements. So again, it tells me something. It's an insight for me. The next step for me, after finding the Jacquard similarity between entitlements, is to basically try to find communities of entitlements with J-car similarity equal to 1 between them, and then define a role for them. For example, I told you that, this is a good example. We have three entitlements, one user, I can define a role. This other one, I have a lot of users, a lot of entitlements. It's a complete bipartite subgraph. I can define a role for it. But I need a way to be able to find such communities in my graph. So the next thing I'm going to do for this, I'm going to run a community detection algorithm, again, from the graph data science library. And this community detection algorithm is called weakly connected components. It's out of the box supported from graph data science library. And there's nothing complex or customized here. I'm simply running that graph algorithm. And now, if I go back here, I refresh my data. I change the perspective again, just to make it easier for you guys to see what I did. So now, every color here, except yellow, is a role. For example, these orange nodes, these three entitlements, because they have the same color, they belong to the same role. Or in this other subgraph, all the green nodes, they are telling me that we could define a role for this subgraph. And here, this was the problematic situation. We had four entitlements, and unfortunately, we could define one role for them and one role for the remaining entitlements in that subgraph, because this was not a complete bipartite subgraph. And the other interesting situation is this other subgraph. We have four users and three entitlements. And because the set of users for these entitlements are slightly different, we could not define a role for them. And for that reason, you can see three different colors for these three entitlements. So how can we fix this problem? Because based on what you see, these entitlements are quite similar, but not exactly similar. So let me go back to my slides. To fix this problem and address this issue, we came up with a different solution. And I'm not going to get into the details of this solution, but I will give you some ideas on how it actually works. Again, we have a set of users, entitlements, and connections between them. And what we're going to do in this second solution, we want to find similar user entitlement assignments. Previously, in solution 1, we found similar entitlements. Now we want to find similar user entitlement assignments, which are represented using edges in our graph. So what we do, we first create a dual graph where each node in this new graph is actually an edge in the first graph. And it shows a user entitlement assignment. And nodes are connected based on some rules. If we have similarity between those two user entitlement assignments, for example, if they are defined for the same entitlement or for the same user, they will be connected in this new dual graph. And now the goal is to find complete subgraphs here. And a complete subgraph is called a clique, which means all nodes are connected to one another. And in this example, this is one clique that we could find. Now, if we want to implement this in our Neo4j instance and run an algorithm to achieve this, we can again use another algorithm from the graph data science library. I'm going back to my Neo4j admin console, and I'm gonna first make sure my graph is clear. I'm gonna reset all the roles that I have created so far. And then I run another algorithm from graph data science library to find clicks. But what you can see here that I'm using a graph coloring algorithm, because the problem of finding maximal clicks in a graph can be transform to the problem of to the basically graph coloring problem. That's why I'm running a graph coloring algorithm from the graph data science library. So I'm going to run this, and I'm going to go back here. Let me just make sure that this is done. Okay. I'm going to change my perspective and then refresh my data. So what you can see that the result is very similar to the result of the first solution. But there are some advantages. For example, for this particular subgraph, we previously had to define three separate rows. But now, because these two are of the same color, that means we could define one role for them. So this is a stronger solution. It can give us basically even a role hierarchy. And I'm not going to go into the details of that, but I just try to show you how you can use all these different tools that you have to basically do role mining in your graph, to find roles based on similarity between entitlements. I'm going to go back to the slides. So we talked about these two solutions for this problem. And we started working with this graph of users, entitlements, and edges, which are user entitlement assignments. Now the question is, if we have such a graph, and if we add more data to this graph, for example, if we bring in resources that are going to be accessed by users, if we add user attributes, is it possible to use this graph to decide if an access request, in real time, should be granted or rejected? Can we do that? Can we, when we get a request for accessing a resource, can we run a query against this graph? And if we get back something, we say that, okay, the request should be granted, otherwise rejected. The answer is yes, and I'm going to explain, how we do that in the second story. The second project or story that I'm going to explain here was with a client called NLX. And in this project, we actually designed a graph-based authorization solution together with our client. NLX, which is part of the NL company, NL Group, basically, is a leading provider of energy intelligence solutions, and they have multiple software services that they offer to their customers. They have a lot of IoT devices in different places, and then they collect data from all these IoT devices, for example, thermostats, smart lights, smart locks, and things like that. And then they analyze the data that they collect. And for example, when there is an increase in energy consumption, they can give you some recommendation that maybe if you do this, if you turn off some thermostats or if you turn off some smart lights, maybe you can meet the demand on on a particular day, for example. And for that reason, they need to actually manage a complex mesh of interrelated users, services, and also IoT devices and things. Now the question is, why NLX started using graphs and Neo4j in the first place? Based on what I explained earlier, NLX is now dealing with lots of devices that are connected, and they need to maintain a real model of the real-world customers. For example, let's say they have a customer called Share Workspace, and this company is working in different countries, across different states and cities. In every city, we have a few sites, and in every site there are a few buildings. Every building has several levels, and then there are all these smart devices in those levels of buildings. For example, again, thermostats, lights, and things like that. So what you saw earlier, this this is called a context hierarchy. And it tells us that the devices belong to this geographical hierarchy, but they can also belong to other parallel hierarchies. For example, there could be another hierarchy that starts from a brand to product lines, and then sensor types, firmwares, and then finally it gets to the devices. So it can get very, very complex. And this is just a part of the graph that NLX needs to maintain. And again, this is called a context hierarchy. At the same time, they have some offerings, right? They have packages of applications and sub-applications. And finally, all these sub-applications, they provide some software services and features. This resource hierarchy needs to be stored somewhere, right? And it is connected to the context hierarchy through licenses. For example, if a city purchased a license for a package of software services, then there will be an edge between that city and the package of services, and we label it with license, for example, just to show that there is a license. Now, to maintain this data, Neo4j was selected as the data storage solution because, it's a native graph database, it's fast and scalable, it has this powerful graph optimized query language called Cypher, and it is the most mature graph database in the market. So for that reason, Neo4j was selected as the data storage solution. Now, what is the problem that we are trying to solve? We are trying to basically find out how we can make sure features, all these software features, they are accessible to those users who have the right privileges. And in addition to that, we want to make sure that we can enforce licenses. So if you even have a role that lets you access a software service or feature, if you don't have the license for it, you should not be able to access it. So we want to enforce licenses too. And the solution that we proposed together was basically a highly granular access control model. We tried to change this graph model to be able to support such a fine-grained access control model. Let's go back to the graph model that we saw together. What you see on the left-hand side is called the context hierarchy. On the right-hand side, we have the resource hierarchy, and they are connected through all these edges that are basically licenses. Now, if we have a user who is trying to, let's say, exercise a feature called read device on a particular thermostat, for example, so that is the access request that we receive. How can we find out whether that access should be granted or rejected? Now, to inject more data into this graph, to make it work with our IAM platform, Identity and Access Management platform, the first thing we did, we added a role hierarchy, which are these blue nodes in the graph, in this picture. They are basically like regular roles, but they bind and they collect some software features together. For example, you can have a role called device admin that is connected to read device feature, set temperature for a thermostat, and things like that. So you define roles for that purpose. We also defined a new node type called grant, which basically binds a role in a certain context to a user. And now when you receive a request, for that user to exercise read device against that thermostat, we need to first find all the grants that have been given to this user, then find out whether there is a path from the grant through the role hierarchy all the way to the feature he's trying to exercise. And then find a path from that same grant node to the device the user is trying to access. So far, we know that the user has the right privileges to access that resource. But we need to eventually find out whether there is a license there. There is a license purchased by the customer to make that feature accessible in that context. If we can complete this, some sort of a loop here, that means we can let the user to access that resource. And this is basically our access policy. You can now write a simple cipher to find all these paths and, in general, find this subgraph. And if that is successful, then access can be granted. This means that now all these access policies that you may have, these are all cipher queries, different cipher queries. Now I'm going to show you, again, another sample graph for this particular example and see how it looks like and how we can, run and evaluate different cipher policies against them. So I'm going to share my screen again, and I'm going to run a different graph database for this particular demo. And while we are waiting for the new graph database to run, the first thing I'm going to do, I'm going to show you a sample resource hierarchy, a hierarchy of applications, packages, software services, and things like that. And then we will look at a context hierarchy, which is, in this example, a geographical hierarchy. And then from there, we can actually, look at a sample policy. So the first thing, now we have our new graph database up and running. I'm going to run this query to get our resource hierarchy. The orange nodes are packages, and then the red ones are applications, blue ones are sub-applications, and finally the pink nodes are software features or software services that NLX is providing. So this is the resource hierarchy. Now I run another query to see the context hierarchy. And this is part of the context hierarchy. It's not a complete context hierarchy, and we are seeing that only for Illinois. So this state has some cities, and then every city has a few sites, which are these yellow nodes, and then we have buildings as pink nodes, and eventually the blue nodes are devices like thermostat and things like that. We also see this single user called Bob. This one single node that we see, it's our only test user for this subgraph. And I'm going to show you how this user is connected through the grant node and the role hierarchy and resources to the rest of the graph. So let's expand this. We can see that, okay, Bob, this user, has a grant. Let's expand the grant. We can see that this grant is connected to a site. Okay, that's good. So that means Bob might be able to access some devices here. Now we expand the role and we get to a software feature called read device. We continue expanding to get to sub-applications, and then application 1, and then package 1. And we can confirm that we see a license a license edge connected from Chicago to package 1. And what you see here, this confirms that Bob can access some devices because, first of all, he has a role in site 2, and this role, this privilege, cascades in this hierarchy. So he actually has this role in all devices here. And because there is a license available at the city level, again, that license cascades, and it is available here. So Bob can exercise read device feature against these 6 devices that we can see. So this is how we found a subgraph that, some sort of a loop, and now we can say that the access request can be granted. And finally, to show you a sample access policy, uh, so in this Cypher policy, I'm trying to find a user called Bob and then find all the grant node connected to Bob, and then go to the feature he's trying to access, find all the licenses, and overall find that some sort of a loop to decide whether the user can access the resource or not. And if I run this, you can see that we are getting something back, which is all the paths that we traversed in that Cypher policy. So I am going back to my slides. So we saw earlier that now we have all the nodes, users, context hierarchy, grant nodes, resource hierarchy. They are all stored in a Neo4j graph. And we also have some services provided by NLX. How can we now make sure every request that goes to reach those NLX services, all those requests are granted? How can we make sure that happens? To do that, actually, we put an identity gateway, which is a product by ForgeRock, in front of NLX services. So every request that is going to reach NLX services now needs to go through this gateway. We also use the Access Manager, which is, again, another product by ForgeRock, which lets us authenticate users, and we can also store our Cypher policies in Access Manager. And then whenever we get a request from a user, the identity gateway intercepts the request, talks to the Access Manager to evaluate all the applicable policies, and then the Access Manager will run some Cypher queries against Neo4j to make sure that the request is allowed and can pass the identity gateway and reach the NLX services. This is the IAM architecture overall. And this is the end of my second story. In summary, I try to define the problem first, define what identity and access management means, then tell you how relationships could make this problem a lot more complex, and then gave you 2 stories, 2 real-world projects for integrating Neo4j into identity and access management problem to deal with the challenge or the issue of relationships, and how we can basically navigate all those relationships in an effective way, to achieve and have a well-designed identity and access management platform. And I want to thank everyone for giving me this opportunity, and thank you guys for joining this webinar. We have also published 2 white papers for these 2 projects, and there are links here that you can see for and use for accessing those white papers. Thank you.
Wow, thanks, Seyed. That was really great. Really great presentation on security in Neo4j.
Thank you.
So I think we're going to do some questions right now. Again, if you have any questions, please put in the questions tab at the top of your screen. Let me search through and find some good ones. Okay, here's actually a really good one. Is it possible to store access policies in the same graph?
Yeah, this is a very good question, and this is something that we have worked on. So in the picture that I showed to you, which was the IAM architecture for the second story, we had an access manager where we stored all the policies, and then for every different policy, you can have a different cipher. But the other, solution to this, which could be more, solid, is to basically just have one cipher policy. So basically, the way that you traverse your graph is always the same for every type of policy you have. But you can now define and describe your different policies in the graph by adding and injecting more nodes. For example, you can introduce new type nodes to support different types of policies, and that simplifies the whole problem a lot. If we do that, because we will have only one cipher, which is our policy, and then if we need to describe different policies and support different policies, we do that by defining these policies in the graph in the form of nodes and different connections. For example, you can say that I always need to have a path from my subject, which is, for example, the user, to the resource he's trying to access. I always need to have a path from the resource which is being accessed to my grant node, something like that, to make it more general and make it workable with one cipher policy. So totally doable, and it's actually a great idea to do that.
Okay, great. So I went through the questions, and I found one from the first one. It says, how can you make sure the roles you define in the first story are meaningful?
That's actually a challenge when you do role mining, any sort of role mining using any tools. You need to make sure your roles are meaningful. And for that, what we did for this particular client, and I didn't really have the time to go through that phase of the project, but what we did, we tried to find some mappings now between roles that we defined to HR attributes. So for example, we define a new role, we call it finance manager, which is a collection of some entitlements. How can we make sure that this role is actually a role for finance manager? And for that, we had to look at the HR attributes of users. So we started again from users and their entitlements, and we also looked at the HR attributes of those users, and then we tried to find out whether it is possible that for a particular role we can find a set of HR attributes to say that if you have these attributes, you will be given this role. And we were successful in doing that to some extent. And we actually ended up with a probabilistic approach. So if you have, for example, these attributes, with the probability of 80%, you should be given this role.
Great. Alrighty, let me look in. Okay. When using Neo4j for authorization purposes, do you store user info, which is needed for authentication, in the graph too?
It really depends on your on the tools that you have and your architecture. You definitely can. For NLX, for example, we were using directory services, from ForgeRock to store all user credentials, and we still have user profiles in Neo4j as well. So at the authentication time, we talk to that directory service, but when we want to, for example, evaluate an access policy or retrieve, for example, how our user is connected to other entities in the graph, we need to talk to the graph. But it is completely possible to not use that directory service if you have any, for example, any other authentication service tool that can connect to graph. You can also do that. So connect your authentication provider to Neo4j using a connector or whatever, and then you don't need to store your user credentials anywhere else. Also, if you use the authentication service of Neo4j itself, that is also another possibility to just store users in Neo4j and nowhere else.
Okay. So I'm looking at the time right now. I think we have time probably for one more question. So let's do this one. Do you see a trend in using Neo4j in graph databases and access management platforms?
Absolutely. We do see that. And I think that comes from the fact that we see more businesses, um, you know, they start using relationships and adding values to those relationships between different identities in their platforms. And that is the time that people realize that, okay, now that I need to, navigate all these relationships, I need a very scalable and effective data storage solution for this. If I use, let's say, a relational database, then for traversing a two-edge hub, then I need to do multiple joins, and that would be expensive. And so for that reason, I'm going to move to a graph database, and that's the case for identity and access management too, because as I said, in IoT platforms, you typically need to traverse multiple paths and multiple relationships to find out whether a user can access a device or not. And in that case, if you use relational databases, it won't be scalable. That's why we see this trend for using Neo4j, even in identity and access management.
Okay, great. Well, I think that's all the time we have for today. So first of all, I'd like to say thank you so much, Saeed. It was really great having you.
Oh, thank you. Thank you for giving me this opportunity.
Absolutely. And thank you everyone for joining. And if your question wasn't answered, don't worry, someone from Neo4j will be reaching out to you. Have a great day.